Hey there, awesome physics students. Let's talk again about RC circuits. There's a few more things we need to learn. In particular, why are they called RC circuits and why is it exponential decay? So let's start with RC circuit here. We're going to talk about it discharging. So I've charged up the capacitor and then I've connected it so that a current can flow, and the current is going to discharge, pull that charge off of the capacitor and allow it to neutralize the capacitor. Okay, so let's start by thinking about the voltage across the capacitor. And just from the definition of capacitance, the voltage across the capacitor is just Q over C. That's just from the definition of capacitance. But you'll notice that the voltage across the capacitor is the same as the voltage across the resistor. And the resistor follows Ohm's law. V equals IR. That's V equals current times the resistance. But remember, the current here that's flowing in this circuit is the rate at which the charge is moving off of the capacitor, or the rate at which the capacitor is discharging. So I want to put that in there for I, and let me just rearrange this. Q over C is equal to the rate at which the capacitor is discharging times R. Now I want R and C, those are constants. I want those to be together so I can talk about this a little more clearly. So I'm going to divide both sides by R here. And when I do that, I get Q over RC is equal to delta Q, the rate at which it discharges. So I want to circle this and talk about this. So you notice that R and C are together on the bottom here. So this is actually where the RC circuit gets its name. This R times C it's a product. Notice that RC is on the bottom, and that's going to give you of this fraction here, and that's going to give you the rate at which it discharges. So if I make R really big, or if I make C really big, what does that do? That means it takes a long time to discharge. How do I know it takes a long time? Well, if R and C are big, this whole fraction is small. If this fraction is small, that means the rate at which it discharges is small. That means that it's going to take a long time to discharge. It's not pulling the charge off there quickly. Okay? And in fact, because of this, the product RC is called a time constant, and sometimes we use the letter tau for that time constant. If you actually check, the product RC actually has units of time. Resistance times capacitance. There's another thing I want to talk about here, and that is the discharge. Why is it exponential? Why is the rate exponential to discharge this thing? So I want to follow the time and Q and V, and I want to look at the current, but I want to look at this in terms of delta Q over delta T here. Okay, so I want to look at this at first as 0. So at t equals 0, there's some charge on here. But remember, the charge is proportional to the voltage. So that gives you a voltage difference across R, which causes the current to flow. And the current is the rate at which it's discharging. And so this is going to cause this thing to discharge. So let me just blank out this one, because I want to look at how these things are changing over time. Okay, after 1 second, the rate at which this is discharging is positive. That means the Q has decreased. And because these two are proportional to each other, Q and delta Q over delta T, that if this is positive, that means that this is going to have decreased a lot. But if this is decreased a lot, that means the voltage has also decreased a lot, because those are proportional. But if that has voltage is proportional to the current, and the current is the rate at which it discharges, and so the rate at which it discharges is also going to have decreased by a large amount. But if the rate at which it has decreased by a large amount has decreased, that means the charges will have decreased, but not as severely as they did the first time. Now, how do I know it's not as severe of a decrease of Q, t equals 2 versus t equals 1? Well, because the rate at which those charges are leaving has gone down. They're not as furious to get off of that capacitor. And so the rate at which the charge decreases has also decreased, right? The amount of the decrease has decreased. And because of this, Q and V are proportional, the V has decreased, but that means the motivation for the current to flow has decreased. And so the flow of current, or the rate at which it's discharging, has also decreased. But if this rate at which the charge is getting off of there has decreased, that means that, yes, charge is left, but the exodus from the capacitor has not been as severe as it was before. So at 3 seconds, this is decreased, but again, the amount of the decrease is less than it was before. And so on and so forth. This will keep carrying back and again and again and again. And what happens is you get the current, or the charge on here, or the voltage, they all will follow this exponential decay curve. And the rate, the slope of this is decreasing, and that slope decrease also causes the thing to decrease as well. And so you get this, this exponential decay curve, this feedback loop. Okay? All right.